Hello and welcome to this training. My name is Vittorio Franco Libertucci. I work in the Linux CSS team at Microsoft. The objective of this training is to introduce you to Microsoft Azure Container Service, also known as ACS. We will also review the available orchestration tools that are currently on offer with ACS, and that is Docker Swarm, DCOS, and Kubernetes. So let's have a look at the agenda for this training. Firstly, we'll have a look at containers and an introduction into containers. We need to understand container technology before moving on to ACS. We'll have a look at how we can combine virtual machines and containers. Then we'll have a look at the different options that we have available to us to deploy the Docker engine. We'll then have a look at some examples of how we can manage the various components which makes up a Docker engine, and that will be a Docker image, a Docker container, and the Docker engine itself. How do we associate disk space to containers? And then we'll understand the benefits of having a technology such as Azure Container Service now available to us. And finally, we'll have a look at the three orchestration tools on offer with Azure Container Service, and that is Docker Swarm, DCOS, and Kubernetes. So the first lesson is an introduction to containers. Traditional containers allow you to pack, ship, and manage items into smaller agile units. Now, this is the same concept for container software technology. It allows us greater flexibility, agility in managing, shipping, sharing, and installing applications. Container technology has been available in various different operating systems for quite a number of years. Linux containers, or LXC, is what Docker historically relied upon. However, it now makes use of an open source library and driver known as libcontainer. Docker didn't invent containers. Docker has created a set of tools to make it easy to work with the container technology. Docker can be simplified and thought of as a tool used to package applications into containers. The analogy often used is to think of containers like a zip file, although they are not zip files. When we standardized on zip, it became easier to share a compressed file. Docker is a way of standardizing the containerization of an application. Please take a moment to review some of the impressive numbers that are currently being achieved by Docker. Here we can observe a representation of a virtual machine environment. We all understand how this works. Virtual machines bring a guest operating system with them. Each operating system has some binaries, libraries, and an application. With virtual machines, you achieve less density in comparison to containers, while stop and start times can also be significantly longer. This is because you have to load an entire operating system. You cannot start a virtual machine in a few seconds, but you do get very good isolation. Each of the operating systems are almost completely isolated. They do, however, share some resources by virtue of the hypervisor. So what are containers? So containers have similar resource isolation and allocation benefits as virtual machines, but a different architectural approach allows them to be much more portable and efficient. Containers, shown on the right, are quite similar to virtual machines, but instead of a hypervisor, there is an engine, known as the Docker engine. On top of our Docker engine, you have binaries and libraries, and these can be shared across different containers. The application is what is unique to your container. You get much more density because containers are smaller. We get faster start and stop times because they do not have a guest operating system. You have less isolation because containers reach down into the host OS in order to be functional. And if you break through the security of the container itself, you can actually get into the kernel. So the trade-off is less isolation, more density, better performance, and greater agility. In this section, we will look at combining containers and virtual machines. By combining containers with virtual machines, users can deploy multiple different virtual machine operating systems, and inside those virtual machines deploy multiple containers within those guest operating systems. We have a Windows guest OS with a Linux guest OS. Inside the Linux virtual machine, we have two containers, applications. Combining containers with virtual machines, fewer VMs would be required to support a larger number of applications. Fewer VMs would result in a reduction in storage consumption. Each VM would support multiple isolated applications, thereby increasing the overall density. So running containers inside a virtual machine enables features such as live migration for optimal resource utilization and host maintenance. In this section, we will now look at the Docker platform and how we can deploy the Docker engine. So here is a high-level view of the Docker platform. There are four main components. First, we have the Docker engine, and this is the program that enables containers to be built, shipped, and run. It's also referred to as a Docker daemon. We then have a client which allows interaction with the Docker engine. It takes the user inputs and sends it to the engine, to the daemon, which then builds, runs, and distributes the containers. Docker images are the third component, and these are read-only templates which are instructions on how to create containers, and they contain instructions on what programs to install inside a container, what folders and files, what network ports to expose. And finally, we have the containers themselves, which are isolated applications. Another component which is not shown on the slide is the Docker Hub. A Docker Hub is an online repository for Docker images where you can search for and download images. So how do we deploy Docker? So in Azure, there are various options for getting a Docker machine up and running. We can use the Azure Marketplace. There's an Ubuntu image available for use. You can build your own Linux virtual machine and install the bits. You can create a virtual machine using Azure CLI and the Docker extension. Again, this will stand up an Ubuntu virtual machine. There are ARM templates available to create a single virtual machine, or you can use the Azure Container Service, which will create an infrastructure of multiple Docker machines. Finally, there's an option on clouddocker.com which allows you to synchronize your Azure subscription with your docker.com subscription, and this allows you to create a virtual machine from clouddocker.com into the Azure infrastructure, and then it installs the Docker engine and allows you to push containers and applications into that virtual machine. Provisioning of a Docker engine from the marketplace is really quite straightforward. Just log on to the portal, go to virtual machines and select Docker on Ubuntu and fill in the information. And in a matter of minutes, you will have a Linux virtual machine running the Docker engine. SSH into the VM and run some Docker commands such as docker ps-a or Docker images. You can also deploy Docker manually in your own systems. These steps run on the assumption that you are currently using either a Linux machine or a virtual machine, and you have access to the system through an SSH client. Here we are installing the Docker engine on an Ubuntu operating system, but you can use other Linux distros such as Red Hat, SUSE, or CentOS. In this section, we'll look at how we can manage Docker containers. So in this section, we will look at how to perform some basic Docker administration. We'll look at how to download an image and that will create your container. How to verify the status of that container and the allocated name. How to restart a container. How do we remove a container from the Docker engine? And how do we remove the underlying image? So now we will actually deploy a container. So obviously the first thing to do is SSH into your Ubuntu machine and become root. So sudo to become root, sudo su. The first command that we're going to actually issue is a docker run command with a couple of switches, -I and T. And what will happen here, Docker will attempt to look for the Ubuntu 1404 image from the Docker public online registry. So that's a image which contains the Ubuntu operating system. So we'll be running a container which will have an Ubuntu operating system. So the -I flag tells Docker to connect a standard in to the container, and the T creates a sudo terminal. So what we issue here is docker run -it Ubuntu 1404. Now, because we don't have the image locally on our Linux machine, the image will be pulled from the online Docker registry. And what you can notice is that once it's completed, the actual shell prompt changes, connected into the container itself. As you can see here, our shell prompt is Ubuntu Docker host, and that is the local machine. We issued a docker run command, and that pulls the image from the Docker hub. And once it's completed, it then puts us into a shell prompt in the container. And the prompt here is root at container ID. Now, had we specified an additional command at the end of this line here, docker run, we could have, for example, looked at disk space or issued a command to look at network configuration. So to verify the status of a Docker container from your local machine, so not inside your Docker container, but from another bash session on your local machine, you can run the command docker ps-a. And that regarding the status of your container. It will show you the container ID, the image, the command that you're running, and in our case, we're running a simple bash prompt, the created time, and the status. Additionally, if you had some ports exposed, you will see additional networking information here. And you can see the randomly allocated name to every container. And our container has been allocated trusting hopper. Now, if you exit the container, you are not leaving the local Linux machine, but you're actually exiting the session of the container. So the container, because there's no other additional processes running against our container in this particular case, what happens is when we exit the container, we are dropped back into our local machine. So you can see that by the prompt changing from root at container ID back to Ubuntu Docker host. We run docker ps-a again, and we see the status is now as exited. To restart a stopped container, we can issue this docker start command. That takes a parameter of -i, and here you can either specify the container ID or the random name that we were allocated, which in our case was trusting hopper. Notice that once you restart the container, your prompt has changed back to root at container ID. To remove a container, we need to ensure that the container is first in a stopped state, and you can stop a container using docker stop command. Once it's in a stop state, you can then issue the docker rm command, which will remove the container from the Docker engine. But be aware, you've removed the container, but the image will still exist in the local Docker registry in your machine. So once you've removed the container, you can verify that the container is no longer available by running docker ps-a. If, however, you run the command docker images, you will notice that the underlying image still resides in your local repository. If you no longer need the image, you can remove it completely from your local registry by using the docker rmi command. And that has a couple of options. You can either use the complete full name of Ubuntu 1404, or you can use the image ID, which can be retrieved by using docker images. We will now look at how we can add disk space to a container. So in this section, we're going to look at two primary ways that you can manage data in Docker. We have data volumes and data volume containers. Now they are slightly different in that data volumes is a directory and data volume containers is a container similar to network storage. So with data volume, it's a directory within a container. Now this is initialized when your container is started up. It is meant to persist beyond the life cycle of the container. So for this reason, the volumes are not automatically deleted when a container is removed. All the volumes are stored on the Docker host. So that means that there's a file system which has these volumes on your local Docker hosts. Changes to data in a data volume will not be reflected in the underlying Docker base image. So data volume container, or otherwise known as a DVC, it's a Docker container, and its primary responsibility is to host a volume and ensure the data is persistent. So volumes can be shared with other containers. So a DVC can be used as a centralized data store across multiple containers on the same Docker host. Other containers can mount the volume inside a DVC and save their data to it. It provides non-persistent containers a mechanism to handle persistent storage. You can add a data volume to a container by using the -v flag, as seen here, -v/data. You can use the -v multiple times to add additional data volumes to your container. You can verify the details of your volumes by using docker inspect and the container name. We can also attach to the container using docker exec -it, the container ID, and bash. And once we're inside our container, we can run a df-h, and we can see that our partition has been created successfully as /data. Okay, so now that we have our Docker container running on our Docker host, I can issue the command docker ps-a, and you'll see that the first container running is our Apache container. This is the name we specified when we created this container. If I want to further inspect the container, we can use the inspect command, so docker inspect and either the container ID or the name. And here we can see the volume that we have mounted. So we have the source, which is mapped to a local directory on the Linux Docker machine, on the local Docker machine, and the destination, which we will see inside the container. We can see here that we have permissions of read write, so we can write files to that partition inside the container. So let's connect to the container. So docker exec it apache is the name, and bash. You see that the command prompt has changed, and now if I do a df-h, we will see that we have a partition as data. Yeah. If we create some more files, file 1, file 2, file 3, we have 3 files here. Now if we exit the container, we've exited the container and gone back to the local Linux machine, and now we'll take this directory and you see we have the 3 files that we created from inside the container. So this is just to show you that the data you created inside the container is actually persistent within the Docker host. Now if we update one of these files, I'm just going to type some text, save it, and go back into our container, into the partition, and we see the data is actually visible inside the container, inside the partition that we've assigned. So if you have some persistent data that you want to share between containers or want to use from non-persistent containers, you can create a named data volume container, and then this is mounted to other containers. You can do this by using the docker create command. So this creates us a container, but it's not really a running container. So we use docker create -v for the volume data store, so it'll be the partition that we're going to be mapping into our additional containers. So here we're creating an additional container. So docker run, and we're using the -- volumes from data store, which was the previous container that we created. We're giving it a name of front end 1. We're creating a second container with the name of front end 2, FE2. Again, we're using the volumes from data store, so everything we created previously. So in our containers, we will have a partition called /data store. Once these containers are up and running, you can obtain the container ID using the docker ps command and can connect to them into the bash prompt, cd into the data store partition, create a file, exit that container, and verify if that file is available in your other container. When you remove containers, Docker will not tell you or inform you about the volumes that are associated with that container. If you later want to remove the containers, you can use docker rm -v against the last container with a reference to the volume, and this allows you to remove the containers and the volumes from the system. You can also use docker volume ls-f dangling true, so this long command here, to find out the volumes which are still on your Docker host, and you can use docker volume rm and the volume name to remove the volumes. So in this demo, I will format an Azure data disk which has been added to this Docker host, and then we will use that data disk as a data volume container that we will then map to other containers. So just as a refresher, fdisk-l will list all the disks on this host. My data disk is this 1 GB SDC drive. So we'll create a partition on this drive. Taking the whole disk. We'll then create the partition, create an ext4 type partition. And here we have created our ext4 partition on SDC. So if we do an fdisk and a device, we do a print, we can see the partition 1. If you do an fdisk-l dev SDC, that will be listed as well. So now if we create a directory called data and we mount our drive onto /data, we see it's mounted here. And now we're going to create our data. We're now going to create our data volume container using this command docker create -v. At this time we're going to use the additional parameter which will map our local drive /data to what we want to actually be shared within a container. So you might remember previously in our slides we only had /data or /data_store, but here we have /data semicolon and another parameter. Now we're going to create a container which is going to make use of our data store. So docker run -d detach mode volumes from our data store container. We've given it a name of fe1. So I'm going to create another container to make use of the same data store. The same data volume container will be used. So now if we do a docker ps-a, we have 2 containers which are running and the third one which has been created. So our data store has been created and front-end 1 and fe2 are running. So df-h, we have /data, and if we go into our /data, which is, remember, the local machine, the local Docker engine that I'm on. So if we touch a file here called local, I'll just leave that as an empty file. Then if we connect to our front-end 1, and do a dfh, we see we have data store, and you see that that is mapped to SDC1. So it's the actual data disk that we attached to the local Docker machine. If we go into data store, we have the file local. and that will just update the file local with the contents, FE1. Cat local. Now, if we come out of that container and go back into our Docker host and look at the file now, local, we see it's been updated with the contents that we updated in our FE1 container. So let's have a look in FE2 and go to the data store directory here, cat local. Again, we see that the file contains FE1. So this is showing you that persistent data can be shared via the data volume container between various containers. Let's create another file here, file 2 from FE2. And then if we save the file, go back to the local machine, and we see we have two files. In this section, we will look at what is Azure Container Service, also known as ACS. We'll have a look at how we can deploy ACS and what are the benefits of having a technology and infrastructure such as ACS. So what is ACS? Azure Container Service. It's a Microsoft technology which optimizes the deployment of popular open source tools and technology. Till now in this training, we have been reviewing and talking about a single virtual machine and a single Docker engine instance. This is obviously not scalable for modern applications. ACS deploys the Azure Compute infrastructure required to host containers in Azure. It deploys a configurable amount of masters and Azure agent resources. The masters are typically Linux Ubuntu virtual machines, whilst the agent resources are based upon VM scale sets. ACS, as we said, is a container management service that manages the creation of all the compute resources otherwise you would be responsible for creating. Its goal is to eliminate the need for you to install, operate, and scale your own management infrastructure within Azure. So ACS will create the virtual machines, the VM scale sets, storage accounts, availability sets, network security groups, virtual networks, network interfaces, and other resources on your behalf. You can use ACS to manage Docker containers on Linux virtual machines in Azure using open source management tools like Mesosphere, Swarm, and also Kubernetes. So ACS is an Azure Compute resource provider, container management service that makes it easy to run, stop, and manage containers on a cluster of Azure virtual machines, together with a master VM that is used to orchestrate your application containers, which are your agents. So basically, ACS eliminates the need for you to operate your own cluster management and configuration management system. It also takes away the need for you to worry about scaling your management infrastructure. So the ACS components, we have a cluster, which is a logical grouping of container instances that you can use to run your application. Agent, the virtual machines that host the containers. An example of a master could be the Mesosphere's master. The master is responsible for sending tasks to the agents. It maintains a list of available resources. The master decides how many resources to offer based on an allocation strategy. There will typically be 2 or 4 standby masters ready to take over in case of a failure. ACS provides infrastructure which could be viewed as one logical computer on which containers are going to be executed. On the left, we see that there are two applications having a number of containers in each. We have app 1 and app 2. When we invoke an orchestrator responds to us by informing us of the available resources. It will take care of running your application for you, and you do not need to know where they are going to run and how they run and where they are executed. The two main deployment options for Azure Container Service is via the portal, or you can even use the Azure GitHub Quick Start templates, which are available for standing up a Kubernetes, DCOS, or a Docker Swarm orchestrator. ACS Engine is another deployment option located on GitHub. It's the code of ACS and allows greater customization, including customizable VNets, attached disks, and multiple agent pools. Using this template generator will enable customers to gain access to the latest and greatest features before Microsoft adds them to the official resource provider. Other deployment options include Azure CLI and PowerShell. When it comes to orchestration, there are various options. You can choose from DCOS, Kubernetes, or Swarm. DCOS is the data center operating system. It is a distributed operating system based on Apache Mesos distributed systems kernel. Kubernetes, designed by Google and donated to the Cloud Native Computing Foundation, it aims to provide a platform for automating deployment, scaling, and operations of application containers across clusters of hosts. And Docker Swarm is a native clustering solution for Docker Engine. It turns a pool of Docker hosts into a single virtual Docker host. The Azure Agents VM scale sets are your Swarm resources. Once your deployment has completed, you will see Azure resources based upon your chosen orchestrator, Swarm, DCOS, or Kubernetes. So the first of our three orchestration tools that we would look at is Docker Swarm. Now this is the native clustering software which is available to Docker Engine. So one of our orchestration tools is Docker Swarm. Now Docker Swarm is native clustering for Docker. It turns a collection of Docker hosts into a single virtual Docker host. A Swarm cluster is achieved by pulling Docker containers, and in ACS this is done for you. One of the labs will give you the opportunity to create a Docker Swarm cluster using ACS. Some of the compute components that make up a Swarm deployment include virtual machines and VM scale sets. At deployment time, I chose 3 of both. And so we have on the left-hand side 3 masters and on the right 3 VM scale sets. The ones on the right are known as agent resources to ACS. The ones on the left are known as masters. The virtual machines on the left-hand side are known as the Swarm master. These can be joined together to give a logical master. The systems on the right, the virtual machine scale sets, are seen as one logical Docker engine. You remember earlier on in this training, we were working always with one single Docker engine on one single virtual machine. Here, the 3 VM scale sets are seen as one logical Docker engine. So we can use various Docker clients to manage containers. Now the Docker client can run on Linux, and you can actually use a Docker client in one of the masters. You could use a remote Linux machine. That could be in Azure or a local machine. It could be a Mac, or we can run the Docker client on a Windows machine. So you send requests to the master to manage your containers, which then forwards these requests to the Docker engine. So when you schedule a job or you want to run a container, the container request will be sent to the Docker engine and your containers will actually run on one of these resources. So let's connect to our Swarm master machines. As you can see, I have 3 SSH connections into each of the masters, 0, 1, and 2. Now, this tool that I'm using is known as Secure CRT, allows me to send a command to all of my machines at the same time. So if I do a docker ps-a, you will see that that command is executed on all 3 of these connections. As we can see here, there are 2 Docker containers running on each of the masters. Now these Docker containers, the first one here, manage, and the second one here, console, these 2 containers make up the containers to manage the Docker Swarm. So they are the Swarm masters. They are running on all 3 of these machines. The containers that are pulled into the virtual machine at deployment time have images in the local Docker registry. So if we run the command docker images, we can see that these are the images which our containers are built upon. That should work across all systems. Okay, if we want to find out information about this local Docker machine, you can run the command docker info, and that will tell you that there are 2 containers running on this machine. Give you a lot of information here. Now, if we want to look at the logical Docker engine, which is running on top of our virtual machine scale sets, we need to export a Docker variable. So we can do export Docker host, and it's running on port 2375. And then we run docker images. We'll see that there are other images that have been used within the virtual machine scale sets logical Docker engine. So by exporting this variable, I'm communicating with the single Docker single logical Docker engine running on the 3 virtual machine scale sets. If I now run docker info, what we will see is that we have 3 nodes available, and these are all the agent nodes, all running Ubuntu. Yeah. So we have 3 nodes available in our making up our Docker engine. So what we're going to do now is run a job against our engine. Let's just check if there's any jobs running. As you can see, there is nothing running at the moment. So we're going to do docker run detached mode port 80. I'm going to get the container to run on 8080. So anything coming in on port 8080, restart always. So this parameter, restart always, will ensure that once the container exits, it will come back up. It will restart up again. So this should kick off Okay, now it didn't need to pull down from Docker Hub the image because I had already previously run this, so it was stored in the local registry. And the local Docker registry, we can see that it contains this Nginx snake image. I've already pulled it down earlier on, and it's in the local registry. Now, if we do a docker ps-a, we can see that this is up and running, and we can inspect it, and this will show us greater information. Docker inspect with the container ID. I'm just going to pipe that through more, and this will show you all the information with regards to this Docker container. Now here we can see the port bindings. I want to see which server this is actually being scheduled on. So which VM scale set is this machine running on? So I can see it's been sent to the first machine. Well, it's actually the second machine because they're labeled 01. So if we have a look at the portal, these are the virtual machine scale sets. And we have a look at the instances. We see we have 3. That's great. So we have an instance ID of 0, 1, and 4. Now our job is running on 1. So that's this one here. We're going to deallocate it. And whilst that is deallocating, we can have a look at the container. So you can see that it's exited. And if we do a docker info, we still have 3 nodes, so that's still deallocating. Okay, that has now finally deallocated. Let's go back and look at docker info. We now see we only have 2 nodes. Docker ps-a will show us that the container is actually gone. So let's start that machine back up. Okay, so that has come back. And now if we look at the docker info again, info. Okay, you should see 3 nodes. There we go, 3 nodes. All 3 of them up and running, showing healthy status, healthy, healthy, healthy. Now, our container should be up and running. Okay, so here we go. Our container has restarted again due to the fact that we specified -- restart equals always when we executed this container originally. So we can also manage our Docker engine from remote clients. So if we had a local Linux machine or a machine that we use as our management station, we could use that. So let's connect to another Linux machine. And we become super user. I'm going to go to the var temp directory, and this is where I have stored the private key for my deployment. So this command will use SSH protocol using the private key, creating a tunnel using Azure admin, which is the administration account which I set up at deployment time, into the remote machine. So now if I export the Docker host variable on this machine, and run Docker images, we should see all of the information pertaining to the VM scale set machine, the single Docker engine that we have. Run docker info. Okay. Now this is also possible on Windows. So if I use something like PuTTY and show you where we set up the tunnel. So this is our Docker Swarm profile in PuTTY. Creating a tunnel, always using the same port 2375. Again, using the private key, open. So that's created a SSH tunnel. If you look at event log, shows you that the port forwarding has been set up. Now, if we open a Windows command prompt, again, I have a Docker client installed on this machine. Now, if I run docker ps-a or Docker images, it won't know what to connect to. So what we do here, we just do a set docker host. Oops. 2375 and run docker images, docker ps-a, and we still see our single instance here running. And if we run docker info, or actually we could run docker inspect. And you can see information regarding that container. Now I'm using port 2375 and you may be asking yourself why. Now if we exit, connect back in again, I just want to make sure that I have unset my variable that we set previously. So if we do docker ps-a, we see these two management containers. Now if I do a process listing and grep for this process here, for this container running here to manage, we can see that this is actually advertising on 2375 on this IP address. Now this IP address is bound to the local network card on this machine. And you can further see that 2375 is sent to 2375 locally on this machine here. So these are the Docker ports which are exposed. So now we have a container running on our Docker engine. Exposing on port 8080. We want to actually connect to that container and see what's running. So let's go back to the portal. This is the Swarm deployment. Let's find the Swarm's public IP address for the agent. And it should be this one, Swarm agent IP, public IP address. And we go, the DNS name is here, we can get that. Now if we start up Edge or a browser, plug that in there, you can see this is now running in our Docker container. So the next orchestration tool we will look at is DCOS by Mesosphere. DCOS is the data center operating system. It's produced by a company called Mesosphere. It is a distributed operating system based on the Apache Mesos distributed systems kernel. Now, Apache Mesos abstracts compute resources such as CPU, memory, and storage to provide resources management and scheduling across your entire data center and clouds. Your data center could be thought of as one large computer. It aims to make it easy to build distributed applications, frameworks, and shared data center resources. Effectively, these are the main components of DCOS. Have Docker, which is the supported native execution engine. Exhibitor is an open source program written by Netflix to simplify the management of another program called Zookeeper. Zookeeper, an open source project too, is used to provide a centralized source for configuration, state data, synchronization, and other options. Mesos, again, from the Apache, uses Zookeeper to store its stateful configuration data, also used in the election process if a master becomes unavailable. Marathon is a cluster-wide init and control system. It contains the definitions of how to run applications and monitors their health, restarts them if required. And Kronos is a fault-tolerant job scheduler, and this can be thought of similar to crontab in Linux or your task scheduler in Windows. So DCOS functions as the data center's kernel, taking requests for resources and allocating the correct resource to the correct application. So on completion of your DCOS deployment, when you go to the portal, you'll see many components, including master nodes, VM scale set machines, which are your agents, load balancers, network interface cards, and some storage accounts, VNets. So all of these components make up your DCOS infrastructure. Now what we're looking for is the FQDN DNS name of my master, which I need to create an SSH tunnel to the master so I can then use the web interface. So here we can see the FQDN. This is the name we use at deployment time. So this is what I'm going to use to create my SSH tunnel. I'm going to create the SSH tunnel using PuTTY on a Windows machine. So here I have a profile already configured for this DCOS machine, which is version 1.8. Previously there was a 1.7 version in the Azure portal. Load the profile. So you can see that this name is the fully qualified domain name. I'm going to use port 22, which is open. Most importantly, we need to ensure that we're using the private key, which we generated with PuTTYgen when we created the DCOS deployment. So we specify the same key here. And the tunnel that we're going to set up is going to send traffic from port 8000 on my local machine to port 80 on the DCOS. So let's open up the connection. And if you right mouse at the top here and have a look at event log, what you can see is that port forwarding should be set up. There you go. Local port 8000 forwarding to port 80. Now this again sets up our SSH tunnel, which now allows us to use our web browser to connect to port 8000 to the DCOS GUI interface. So now that the SSH tunnel is configured, we can go to a browser and look at localhost 8000 and authenticate with the DCOS framework. You'll have a set of configuration options down the left-hand side. The dashboard will show us the state and the health of our system. And what you can see here in the middle is that I have a couple of applications running. I have a Marathon load balancer and I have an application which is a Docker container application, Hello World. If we look at the nodes, we can see The agents, which are a mixture of private and public IP agents. Here, the universe section allows us to see all of the frameworks and applications that we can deploy onto our DCOS. System gives us an overview of our configuration and all of its components. Now let's go back and look at services. So I have a Hello World application running. And from here, you can see that we can scale it up, restart, suspend, or destroy. It's currently running 3 copies of Hello World. You can see that here, 1, 2, 3. So we want to see how this application is responding. Let's click on one of these apps. See that the endpoint here, VFL DCOS Agents North Europe, Cloud App Azure.com. That is where our application is going to respond. So I'm going to use that. And you can see we have Hello World. Now we have 3 copies of it running. So if you take note of the host name, 66C, refresh, we get F27 and D10. So you can see that the load balancer is performing fine. And we can scale that down or up. So let's scale it up to 5. You can see that that's now running 5 versions of Hello World. Okay, we also have a DCOS client, which allows you to interact with your framework, with your DCOS framework, using a DCOS client on Linux or Windows or Mac. So this is the Windows version. So as you can see here, we have a couple with the command DCOS. Will give you the help of the various options. You can run DCOS node. I'll show you some of the node information that we saw earlier before on the GUI. DCOS task will show you there are now 5 copies of Hello World running with 1 load balancer. And we can do something like DCOS marathon app list, and that will show you how Marathon is monitoring the health and the status of these applications. If you need greater information about one of these applications, app show Hello World. So this gives you a JSON output format of the application which is running. The third and final orchestrator that we now have in ACS is Kubernetes, and that originally comes from Google. Kubernetes is another orchestration framework which we released very recently, preview November the 7th, 2016. It's an open source system for container orchestration, and it runs Docker containers. Now it's similar to DCOS, where it ensures that containers run continuously, and it can be run on cloud or on bare metal. The automatic placement of containers where we can run our containers most efficiently is, again, another feature similar to DCOS. So let's look at some of the concepts for Kubernetes. So you have clusters, which are the compute resource on top of which your containers are built. We then have pods, which are a small group of Docker containers that work together. So this is the smallest deployable item. We then have replication controller. This ensures that the exact number of pods are running. So for example, if you require 4 pods to run and should a pod die, Kubernetes will spin up an additional pod. Services are a set of pods that work together. So for example, a load balanced back end or front end could be considered a service. And labels are used to organize and select a group of objects. So a graphical representation could show containers running various applications. And these containers work together and they are placed in pods. Pods can be placed into services. For example, on the left-hand side, we could have a service which contains web services, whilst on the right-hand side, we could have a database service. We can then place a label around our services, such as front end. So I've connected through to my master of my Kubernetes deployment. Every machine which makes up this deployment has a set of processes on there which are common to each of the VMs. There's the Docker container, there's a proxy, and there's a kubelet process. I can use the kubectl to interact with my infrastructure. So kubectl get nodes will show the machines that are making up this deployment. We can have a look at any running services. kubectl get services. We see Kubernetes is running. That's the master process. We can check if any pods are running. kubectl get pods. Now let's try and start up our first Docker image by running kubectl run nginx, and we're going to use the image nginx. So you notice that has created a deployment. So if we do a kubectl get deployments, we have a deployment called nginx, and we have a pod called nginx. We do not yet have a service. So this has started a Docker container in a pod on our node. So the next step is to expose the nginx deployment as a Kubernetes service on the private service network. So we can do that. kubectl expose deployment, the name we gave the deployment, and the port. If we now run a kubectl get service, we should see this as a service. Now the final step to expose this service to the world is by changing a configuration parameter from cluster IP to load balancer. And we can do this by running kubectl edit svc, a service, and the name nginx. So we're looking for the type cluster IP, and we're going to replace that with load balancer. This will now cause Kubernetes to create an Azure load balancer with a public IP. So if we have a look at the kubectl get service, we now see that this is pending, and eventually we'll get an IP. Okay, so now you can see that the Nginx service has been assigned an external IP. We can use this IP now in a web browser. So if I put that in Edge, we can see that our web server is responding. We can also manage our Kubernetes deployment from a Windows client. You can download a executable, put it in your path, and you can run commands against your Kubernetes deployment, kubectl get nodes or kubectl get services. Now we can get access to a dashboard, a browser interface, which is quite nice. Kubectl proxy. And we refresh that. So this is our dashboard. We can see services are running, pods. You can schedule jobs. And it's quite a feature-rich interface. To summarize, a Docker engine allows you to pull images which are used to create and run containers. Docker engine can be installed using various options. Azure Container Service simplifies the deployment of container and microservices orchestration tools, which you would otherwise have to install and configure manually. The three orchestration tools currently available in ACS are Docker Swarm, DCOS, and Kubernetes. Each of these have a command line interface which can be used on either Mac, Linux, or Windows.